in 5 seconds.
Hello, ladies and gentlemen. It's my great pleasure to welcome you to the TUM AI lecture series. Today we have a very distinguished speaker again, Max Welling from Amsterdam. A few words about Max. He's very well known in the field of machine learning. He's been very influential in NeurIPS, IStats, MIDL. He's also fellow both of the CIFAR, Canadian Institute of Advanced Research, and of ELIS, the European Lab for Learning and Intelligent System. He's heading an ELIS lab in Amsterdam, very engaged there as well. He has written numerous papers on many areas of machine learning. In particular, he's known for autoencoding variational Bayes, an extremely influential paper, but also he's known for graph convolutional networks for classification, semi-supervised classification. Lots of work also on Bayesian learning, convolutional networks. And so he's also received many awards, including the ECCV Kundering Prize in 2010. It's a great pleasure for us to have you here, Max. The floor is yours.
Thank you, Daniel. And also I'm very happy to virtually be at the ELIS unit in Munich. That's very nice. So today I'm going to talk about our work within the lab on symmetries in inference and learning. And this is joint work with these folks here. You will see them in the slides as well. So the overview of the talk is we'll first give a little bit of an introduction in symmetries and equivariance. Then and then I'll talk about, oh, I guess that fell off. So there is a section then on graph neural nets, equivariant graph neural nets. Then there is a section on MCMC written as an ODE. And sort of actually these are deterministic MCMC algorithms. I'll talk about deep learning as a partial differential equation. And if time allows, so I'm not sure precisely how much time I have. Is it 45 minutes or for the talk? Yeah. Yes. So if time allows, I'll talk on quantum a little bit and show the latest work that we did there, and then I'll conclude. So this is a teaser plot. So this is Gibbs, Joshua Willard Gibbs, and shown as a sort of a probability image where light colors are high probability. And here we are sampling using an independent sampler. Every sample is completely independent. And then here is our sort of dynamical Gibbs sampler, which is a deterministic ODE, which, as you can see, has very different properties, but samples actually very efficiently. More on that later. Just as a reminder, to get everything on the same page, we'll be talking about convolutional neural networks in the first part, and graph neural nets, which are introduced later. And the convolutional neural network is basically, you have some data which lives on a sort of 1D or 2-dimensional sort of a geometric plane, Euclidean space. And we have some filters that we slide over the image and take inner products between the filter values and the underlying pixel values of the image. And we sum it, and then we store the value here in a feature map. And we do this for different filters, so we get different feature maps. And then there is often some pooling operation where we reduce the space, size of the space, and then we repeat, so do another convolution, so we get more feature maps, etc., etc. And then in the very end, you typically have some kind of, there's non-linearities in between, clearly. And in the very end, you have some kind of multi-layer perceptron to then predict, let's say, a bunch of classes. That's the forward pass, and in the backward pass, you basically look at some errors between what you want to predict and the ground truth. You compute the derivative of that error with respect to, say, a parameter that's sitting here in in one of these filters, and you compute that by backpropagation through this entire sort of neural network, and then you make your updates and you learn. Now, most work has been done in sort of convolutions, convolutional neural networks in Euclidean spaces, like 1D or 2D or 3D, like for MRI, let's say MRI volumetric data, or even 4D if you have like also the time component. But there's also data which lives more naturally on domains which are not Euclidean. For instance, you might want to study wind patterns on the Earth. So that's a sphere. And so one question that arises naturally is, could you define a convolutional neural network on a sphere? Right, and there's some issues. I won't go into those today, but you can indeed, and we've done work on how to actually define a convolutional neural network on a sphere. There's other data structures that we are interested in, for instance, graphs. There's a lot of graph data out there, molecules of graphical structure, but also social networks, even point clouds, like you can represent three-dimensional objects as point clouds, etc. And so the question is, how do you do deep learning in some way or other on these non-Euclidean data structures? And of course, there's a huge number of applications, more arising every day in these sort of in this field of geometric deep learning, in computer vision, graphics, social networks, chemistry, biology, physics, medicine, etc. So let's first say a few words about symmetries, which is the motivation for this whole idea around equivariance. And it basically comes from physics. Now, in physics, people have figured out that if you sort of change the perspective of the observer, like the frame in which the observer makes observations, for instance, because it's moving relative to another frame, you want that the underlying physics that you described doesn't change. You're still looking at the same phenomenon. However, people might interpret the things that they see in different frames very differently. For instance, a figure that is standing still and looks at a point charge describes that using an electric field. Now, if there's somebody else who flies past that point charge with a particular speed, then that person will actually interpret exactly the same physical phenomenon as a magnetic field plus an electric field. And so these seem to be two distinct phenomena, but the only way they're distinct is because they're described by people who are in different reference frames. And in fact, if you all sort of unify that, you get to Maxwell's equations and to special relativity. Now, if you take that one step further, Einstein basically said, well, not only are the phenomena described by two frames which are in relative motion with respect to each other, let's say constant motion, the same, but also if you are accelerating. Now, if one person is accelerating, that person feels a force clearly, and that force is actually equivalent to the gravitational force. And the reason is that if you're in a box and you feel that force, you cannot distinguish between these two situations in any way. So it's really a symmetry, just describing nature, the same phenomenon in two different ways, in two different reference frames. And so this idea of symmetry is extremely powerful. In fact, the whole standard model of all our fundamental particles is actually built up of these groups. It's organized according to these groups. There is, leptons and quarks and all these kinds of things, and they're sort of representations from, that transform according to these different groups, like U1, SU2, and SU3. And so the thing I want to say is that this came out a bit weird, but the thing I want to say is that symmetries play an incredibly important role. Now, what we're going to talk about today is equivariance, and that's basically the idea of encoding these same symmetries in a neural network in the way that physicists do it in their equations. Now, the idea is that if you have, let's say, some space, let's say this could be your image, and you do a transformation on that space, which could be your convolution, like depicted here. And if you take that image, you could also do a symmetry transformation. In this case, it's a translation, but it could also be a rotation of that object. Now, if you now first do a symmetry transformation and then do the convolution, or first do the convolution and then do the symmetry transformation, that's what we call a equivariant map. So first f and then phi, or first phi and then f. Note that phi I lives in this y space and phi x lives in this space. If this holds, we say that the map is in fact equivariant, and that has all sorts of very nice properties. Of course, it puts a constraint on these maps f. For translations, it means that this f needs to be a convolution. It puts all sorts of interesting constraints, and it has all sorts of interesting properties, among which the fact that you have a lot less parameters to learn. So it's very data economic, but also that the next layer now has a much easier way to detect patterns in the layer below. Because if I undergo one of these image transformations, I don't get some random permutation of all my activations. I get a very structured transformation of these activations, which means that the next layer has a much easier time discovering patterns again. And so if you layer these things, it's a lot easier to sort of learn from these neural networks that have this property. And you might think that, in fact, these neural networks might, the convolutional neural networks have this property for translations. You might think that they also have this property for rotations. But in fact, it's not true. So here's a nice visualization by Daniel Worrell, where you take an image and it's in front of a camera, and then you rotate the image, and then you study the feature maps. Now here's the feature maps as they go around inside the camera, and if you stabilize the image, which means like you rotate with the camera, then you get this. It's copied here. So you see that as the camera rotates, these feature maps are changing a lot. Where if you would have an equivariant map, they should remain stable. And this is what you are seeing here. So this is one particular model that they worked on that was actually a rotation equivariant neural net. Now, I won't go a lot deeper into this topic and how to, there's a huge amount of things to say about it. But the good news is that, in fact, there is now a very simple way for you to, if you can identify the group that you're interested in and the representation of that group that you want your features to transform under. And in fact, you only need the generators of that group, which is often a much, much smaller number than the actual group elements themselves. And it holds for both continuous Lie groups as well as for discrete groups. For both of them, you would just need the generators. Then you can stick this in a piece of code that Mark Finzi here developed, and you can actually get an equivariant basis of convolutional kernels out for that group. And that's very nice because you can then basically get your filters, a basis of filters, and you can just learn the actual sort of coefficients which multiply these kernels, and then you're guaranteed to have an equivariant convolutional neural network. And when you have to think about the nonlinearities, obviously. And here's an extreme example. This is Rubik's Cube, and it has a total of 4 times 10 to the 19 elements, or more than 4 times 10 to the 19 elements in its group. Yet it has only 6 generators, and so if you stick it in this code, you can actually get the basis for that particular group. And you can do the same thing with the symmetric group. It has n factorial elements, but it is only like n or n minus 1 generators. And basically with many other ones, you can use things like SUN or the Lorenz group, or all sorts of other groups you can apply this code to. So it's in some sense it's become very practical these days. Okay, so then let's make the jump to graph neural nets. Now we can interpret a normal convolutional neural network. In fact, we can interpret it as a message passing scheme. So if you think about what a convolution was again, so you have a filter that you slide over the image, and you take the inner product of the filter coefficients with the pixels of the image, and then you sum them up and you store the value here. You can think of that as, let's say, if you would have a whole stack of feature maps here, by basically saying that you have like a vector living on each one of these nodes, which correspond to the different feature maps. And this would be 1 pixel in these feature maps, but sliced across the channels. And you would multiply this with a particular matrix W1, which you cut out of all the filter maps that you have, all the filters that you have. And you do this for every neighbor with different matrices W, and you even have one matrix for yourself as well. And then you multiply these matrices with these vectors, and then you sum up all the values, and then add a bias, and then push it through a nonlinearity. And then you do the same thing exactly. You go to the next, one. Let's say this one, and you look at its neighbors. You do exactly the same thing, and you use the same, matrices W here. So that's just a message passing interpretation of what a normal convolution is. Now, for a Euclidean space, you can basically state that you always have the same neighbors, right? There's always going to be, 1, 2, 3, 4, 5, 6, 7, 8 neighbors, and they will always have this particular orientation. So you can distinguish them, and you can sort of use different matrices for them. Now, what do you do if your data is not like this super regular graph, but is a much more irregular graph? Now, in that case, it becomes problematic to have sort of different matrices W, because you first of all, you don't know how many neighbors you're going to have, and the ordering is not determined, because I could just take this particular node and I could move it right here, and it would now be in different position in the ordering. Let's say if I go clockwise around sort of the neighbors, but where this thing is laid down on a two-dimensional plane is not written in the specification of that graph, which is just connectivity matrix. And so it's very hard to sort of see how you would give different colors, use different matrices for all the neighbors. Now, I should say we have done work with Pim de Haan and Taco Cohen, which are called natural graph networks, where we can in fact design these filters to be non-isotropic, which means different for the neighbors. But I'm not going to talk about that today here. So for now, we're just going to take this sort of simple solution, which Thomas Kipf and I introduced in, what is it, 2016 or something, to use the same messages here. Now, there's a slight generalization of these graph neural networks, which is slightly more powerful, which is, again, to think of it as a more general message passing scheme, which is that we're first going for every edge. We're going to compute the message, let's say from I to J here. We're going to send a message here from I, in this case, from I to J here. It depends on the features at node I, it depends on the features at node J, and there might be some edge features which are sitting here. And we can take any sort of MLP, any nonlinear function of these things, and we compute the message. Then in the next step, we sum all these messages which flow into this node I. So we sum them all up. And then finally, we take that message, that's sort of the sum of these messages that are coming in, plus some node features, plus the actual, so these are fixed node features, plus the actual evolving node features, the embedding vectors. Again, we push it through another nonlinearity to get the update for the node at HJ. So this kind of message passing interpretation of a graph neural net is more general, and is mostly, I guess, used for graph neural nets. Now, what we did, so this is new work. What we did was inspired by the problem of modeling molecules, which are some sort of graph. But this is sort of a graph that lives in a three-dimensional geometric space, right? So it's a graph embedded in a three-dimensional space, which means that every position of that molecule, we can assign you basically 3 coordinates in space. And we wanted to say, and the task could be, I have a molecule, I get the molecule in an arbitrary position and orientation, and I need to predict of, properties of that molecule. Let's say, does it bind to a particular catalyst or something like that? Now, clearly we know, translation or rotation of this object shouldn't really matter for predicting the properties. And then there's other, so we're going to try to make this network equivariant under rotations. And the other thing is that we also have a number of properties which could be like atom number, interaction type, that live on these edges, which are these A features that I talked about before. So here are these A features, A here, and here's these features here. And we have our embedding vectors H, which we update at every iteration, but these are invariant under rotating the molecule, right? So what is the equivariance that we desire? We say, okay, we start with the molecule, and we may actually also have vectors here, which could be, let's say, the forces on these atoms. Now, if we rotate this molecule around, then, for instance, if you look at x2 here, points out, so we see that x2 moved here, right? So we just rotate everything, including the forces. We rotate the whole thing around. Now, this particular, x2 distribution is now here, but it's exactly the same. So that hasn't changed, right? But these vectors, they actually rotate as well as the x's rotate. So if we first rotate the molecule and then do our update, let's say our convolution update, message passing update. Now, under a message passing update, well, everything changes, right? Because these distributions here, these histograms change under an update, as well as these forces, they might change, as well as these locations, they may change, right? Everything might change a little bit. Right. Now, equivariance means if I rotate and update, it should be the same as first updating and then rotating. That's the equivariance condition. Okay, let's see how that could look like. So first of all, the state of the system is defined by these scalar features H on every node, and the position features X on every node, and the force or velocity or whatever vectors V on every node. Then there is sort of fixed features like atom number, interaction type, etc. And then we have the things to update here are, the invariants of the problem that don't transform under rotations are these H's, which are the actual, these invariant features H, and the distances xi minus xj. We will, those things, if I rotate, then the norm doesn't change. Okay, and then I'm going to define a generalized graph neural network that works as follows. Again, it's a nonlinear sort of map that takes in the scalar features at level L for node I and for node J. I'm going to compute this message on an edge. It also takes in these invariant distances between the two molecules and these invariant features Aij. So Mij does not transform under rotations. Then I'm going to update my V. So V is going to be updated like an invariant factor times V plus this kind of difference vector, which does transform, but as a linear factor. So it transforms sort of with a linear matrix in front of it, times another invariant. I do an update on my axis by let's move them by an amount V, which is sort of the speed. I now aggregate all the messages, and I do another update on my node based on the aggregated messages and the invariant embedding vectors. And then I repeat the whole process. Now, it's not hard to show that, clearly, if you remove the V's and the X's, you'll just get back to the GNN, to the graph neural net. But the other thing is that it's also not hard to show that this thing is actually equivariant, because basically X and V, which are the vectors which transform under the rotation group, they appear linearly. And so that actually transforms nicely. Okay, so we applied this to a number of problems. So first of all, you can apply this to n-body simulation. So here the idea is that you have a bunch of trajectories, and you need to predict the future of these trajectories, right? So if we apply, so here we train this particular graph neural network, and then we predict the future trajectories by just moving X further into the future. And sort of we, compare it to a whole bunch of other models in the literature, which are also equivariant or non-equivariant. So linear is, of course, very rough, and it's pretty poor error, but it's very fast. The SE3 transformer, which we developed before this model, it's okay, not great for this task, but it's most importantly, it's quite slow. It's quite heavy computation. Tensor field networks, a graph neural net without equivariance, pretty good actually. Radial field, which is a model by Kohler and Frank Noe, also does pretty good. It's equivariant. but it doesn't have the graph neural network, the full graph neural network sort of properties, and sort of we can see that we can do best. So if you compare, let's say, the graph neural net, which learns everything but is not equivariant, versus the radial field, which is equivariant but doesn't have sort of the power of the graph neural net, you can see that for a small number of samples, the radial field is very good because it has the right inductive biases, but as the number of samples from which you can learn improves, in fact, the non-equivariant model, the graph neural net, is actually overtaking because it basically learns to be equivariant. But if you build an equivariance, then you can sort of be best of both worlds. We also applied this to the QM9 dataset. So this is a dataset of molecules where you need to predict properties of these molecules. So here's a whole bunch of properties that you need to predict. And it's, of course, a labeled dataset. And we compare to a whole bunch of other methods to predict these things. And so this model works surprisingly well. In fact, we found that the GNN all by itself performed also pretty well, worse than this. But you know, we are basically outperforming everybody except for 2 of these categories where we take a 2nd place. But this was very encouraging because this is actually a fairly simple model. For instance, compared to our previous model, which used collapsed coordinate coefficients and spherical harmonics, and it was all very complicated. So this is a much simpler model that performs actually a lot better. Okay, so that was the first part of the talk, which was about sort of symmetries. And so we are about halfway in now. So the second part of the talk is about a somewhat different topic, but it's related to the previous talk because I am actually talking about symmetries, although they're of a pretty different kind. So here we're going to talk about the symmetries of a probability density. And we're going to use the symmetries of this probability density to design fast samplers for these probability densities. Right, so I hope everybody sort of knows what Markov chain Monte Carlo means. So the idea is I'm giving you a probability density P of X, let's say, and you're going to have to design some kind of stochastic dynamical system or even a deterministic dynamical system such that if you collect the samples over time, and let's say you're computing averages of a function over, you know, by taking Monte Carlo sums or averages over these samples, then these averages, they converge to the average you would have taken if you would integrate that function over this actual density. Now, the typical way to do that is to build a Markov chain Monte Carlo procedure. And basically, the easiest Markov chain Monte Carlo procedure is one where detailed balance holds. So what is detailed balance? It basically says the probability of being in any particular state, P, times the probability of moving from t to the next state, p x t plus 1, must be the same as, you know, the probability of being x t plus 1 times the probability of moving back. So in pictures, this basically means that you have 2 pipes, and in these pipes, there's probability mass flowing around. And then for any 2 points in space, you compute the probability, the target probability, px, and here is sort of p of x prime. This could be more probability here than there's probability here. And what you want is that it's at equilibrium, the amount of mass that you're moving out from here to here is equal to the amount of mass that you're moving out from here to here. So that the probabilities don't change. In other words, the pipes here carry the same amount of mass. And this has to hold for every pair of points. And clearly, if it holds for every pair of points, then, you know, these probabilities don't change anymore. Yeah, so of course, you have to make sure that the samplers not only satisfy this detailed balance, but you also have to show that you're not, for instance, flipping back and forth. So if you start a particle here, you don't want that this particle just keeps flipping back and forth between those 2 points, because then, you know, the probabilities might not change, but you're not reaching every point in space. And so ergodicity makes sure that there is at least a chance, a finite chance, that you will reach any point in space. And then you can guarantee under these conditions that the equilibrium of this process will sample from the correct probability distribution. Now the problem, and the good thing about detailed balance is it's very easy to design these Markov chains that way. The problem is that it's like a diffusion process. It's like you drop a piece of milk in coffee and you wait, right? That diffusion is very, very slow. And what you really need is something like convection that's shown here. So in convection, the probability mass sort of flows around in circles, but it does it in such a way that if you look in a particular cell, that the amount of probability mass that comes in and the amount of probability mass that flows out are exactly the same, which means that for every cell, the amount of probability mass at every point remains the same. And in fact, it needs to be exactly equal to the target probability that you want to sample from. Now here you can see if this would be a drop of milk and you would stir, right, then the stirring would be much more like convection, and you would mix your particles much faster through the whole space. And that would be a much more efficient sampler. Now the condition, so here is again detailed balance. That's more like diffusion, where T is now the transition kernel. But that's actually, this is too strict of a requirement. Well, we can actually do with a much less strict requirement, which is called invariance. Now under invariance, we're basically going to say, I start with the probability P, and then I move, some mass to probability X prime. If I integrate, all the mass that's coming into X prime from everywhere, then, obviously I can call this P prime. So that's the mass that's flowing into P of X prime. That needs to be equal at all times to the target probability P, right? So if I guarantee this, then the amount of mass in P is exactly equal to the target mass. And it's very easy to prove by integrating basically over T prime, then that this is going to be the condition that you need in order for plus ergodicity in order to make sure that the particles that evolve under T actually distribute under the target distribution P. Okay. Now you might think that so maybe this detailed balance is so how do you design something that is that satisfies this, obviously, because this is a necessary requirement, but there's not necessary this sort of requirement here, which is sufficient but not necessary, and it might seem hard, but anyone that is not of this nature but does satisfy this is what we call an irreversible kernel. And for an irreversible kernel, it's somewhat of a bad name because the kernel certainly is reversible, but it's a different kernel. So the reverse kernel, the probability with which you move backward, is not the same as the kernel you use to move forward. For instance, I can turn the clock around on this, and then let have all these turn these arrows around, and then you would be moving backward. That would be the T tilde here. Now, so in other words, you can always write something down like this, if you cannot always write it down, but if there is a T tilde that satisfies this particular one with this probability P, then if it exists that it leaves P invariant and you're correct, right? So and this if and only if. So if you find such a T that's normalized, etc., then it will leave P invariant. And if there is such a P, you can find such a T tilde. Okay, now we're going to look at a very special subclass of these problems. They're irreversible kernels, and they are deterministic. So the kernel is no stochastic, but it's like it's a flow. It's literally taking an X and moving it according to some function to some definite new position X prime. So it's much more like what you see here, right? You have sort of an ODE, and you're flowing according to these arrows in this ODE, you're flowing probability mass around, but it's not a stochastic process, it's a deterministic ODE. And then, so to build some intuition for, these types of irreversible deterministic MCMC samplers, we want to sort of prove the condition that we require. And the condition is always that the amount of probability that's flowing into a region, any region, has to be equal to the probability that's flowing out of that region, right? So then we get to some a stable condition. And And so this basically means that the divergence of this vector field along which we are flowing has to vanish. And the reason for that is basically Gauss divergence theorem, which says that the volume integral over the divergence of this vector field F is equal to the flux over like the surface of this volume. And so this is basically saying that the amount of stuff flowing out is equal to the amount of stuff flowing in. And this is saying that that's equal to the average of the divergence of this vector field. So if we require that the divergence is 0 everywhere, then we can, for an arbitrary shape, we can guarantee that the amount of stuff flowing in is equal to the amount of stuff flowing out. Now, and then there is, of course, the continuity or the Liouville equation, which guarantees this. So the Liouville equation says that the time derivative of the probability density at point x and time t is equal to the minus gradient of the probability current. And as long as we make this thing divergence free, so this thing 0, the probability is also not changing. Okay, so we can, and this takes a little bit of math, but you can show that this probability current can be written as the probability density times the vector field. And so that's the vector field V. So V is the current divided by P. And then we can write down an ODE for the particles, X. They move over X. And the time derivative, the change of these particles, flows according to this vector field V. And this has to be equal to J over P. And the divergence of J has to be 0. Now, if this is true, so if we find this divergence-free vector field, any divergence-free vector field 0, divided by the target probability density P, and then we flow our particles according to this V, then we're guaranteed, if we also prove ergodicity, then you can actually flow according to these. Then if you flow according to this vector field, then you'll sample from the correct distribution. And we can think of this basically as a set of symmetries. That's the way I think about it. It's transformations. So this vector field is a bunch of transformations on your space, such that if you move your probability according to these flow lines, the probability density doesn't change. So you can think of this as sort of a diffeomorphism type of symmetry of your space. Okay, so then we set out to actually develop a particular instance of this, which was studied before, but not in a very different literature. It was in the chaos nonlinear dynamics literature. And we call this dynamical Gibbs sampling. So here the idea is that we're going to design our vector field V, and we're going to write the ith component Vi to be Ci, which could be a constant, or it could be dependent on everything except for Xi, divided by the conditional distribution P of Xi given X naught I. Now you can do a quick derivation, and if you compute the divergence of the probability current, then you very quickly find out that that's going to vanish under, for this particular definition of Vi. Okay, you can also show that if you pick the right Ci's, then you can get ergodicity, at least for, in lower dimensions. Otherwise, you just have to sort of observe it. And so here we see exactly if you run that particular, algorithm, if you run it, you see, a very, of course, deterministic sort of flow happening that sort of very efficiently samples from this picture, right? Where independent samplers looks like that. And note, by the way, the independent sampler has 0 autocorrelation, so it's the perfect MCMC chain if you want, right? So basically what we did is I think the most useful is this is most useful for discrete distributions. So for this, so think of every cell here having assigned one discrete value. And then we fill this box uniformly with probability mass proportional to that value. And then we basically integrate by having a constant velocity inside this cell, right? And basically reflecting off of these boundaries. And sort of course, they have different speeds in these different cells, and those are weights for the sampler. Okay, so I'm going to show you now. Ergodicity is a bit hard to prove, and it's related to chaos theory. But here you see Baker's map, which is basically also a chaotic map where you can see how the things can mix very fast. That's also deterministic. Now here's some experiment. In this experiment, so here we have the typical 1/square root of n convergence of any MCMC sampler. So we get an independent sampler, which is basically the fastest possible MCMC sampler if you don't have negative autocorrelations. Then there's the Gibbs sampler here. And then we have our sampler, which in the beginning, you know, it's slower because it has this kind of very deterministic type of sort of trajectories. But then, and that's interesting, after some time, the convergence now, the asymptotic convergence is actually better. It's 1/t. So this is a 1/t convergence plot. And that's kind of interesting because it's faster than any random sampler, basically, even the independent sampler has. And so this is probably a feature of sort of the deterministic nature of this sampler. Here's a Ising model example. Sort of here's some other implementation of a sampler, Gibbs sampler, and then the dynamic Gibbs sampler basically very quickly increases the log probability, and the estimation errors also come down very quickly. Now, I think I'm out of time because I'm supposed to talk 45 minutes, and I think it is perfectly fine to skip this part. In one sentence, we did look at how to reformulate a deep neural network in terms of a partial differential equation. You know, we were motivated by the fact that for images, you know, the pixel grid is not always regular. It's more like a graph, as I talked about before. And so the question is, how do you, so you can think of this as basically as a finite sampling of a continuous field. We model that continuous field by a Gaussian process, and then we define a partial differential equation of this kind on this Gaussian process, which is now continuous, where D is a derivative operator with all sorts of, you know, first and second order derivatives, and here's the time order, and basically we integrate that. We for certain choices we can actually exactly integrate that forward, and that implements a convolutional layer on this object. And now we'll just skip basically what that is. So we then also set out to talk about, you know, quantum mechanics, because quantum mechanics satisfies exactly the same equation, the Schrödinger equation. And it turned out that if we go to quantum field theory, and this is no joke, we actually discover particles inside a neural network, which we named Hintons. And although this looks like a super exotic thing, in fact, what we did is formulate a neural network in such a way that you can implement it on an optical quantum computer. So this turns out to be the right formulation of deep learning so that you can implement it with lasers and all these kinds of things on an optical quantum computer. I will leave that for another time and now conclude. Basically, machine learning, we all know, is inductive bias plus data, and I think symmetries are a really good way to infuse inductive biases in your model. We looked at the equivariant neural networks, a quite simple architecture that works very well, and for instance, might have good potential for modeling chemistry and drug design, basically molecules. And we looked at MCMC algorithms, and we're thinking about symmetries that leave the density invariant and then flowing according to these symmetries to develop deterministic MCMC algorithms. And we showed that they have very surprising convergence properties, which are faster than the typical 1/square root of n convergence. And then I talked a little bit about CNNs as partial differential equations, but I didn't go into any detail. And with that, I will hand over back to the chair, to Daniel, for questions.
Thank you, Max. Thank you for this wonderful presentation and all the amazing results. Very nice presentation. I think we can open the floor to questions. Does anyone have a question? Maybe I'll start with one, if I may. Sometimes that helps to kick off the discussion a little bit. You talked about how to construct equivariant graph neural networks, but typically this requires you to know what the invariance or equivariance group is, the group transformation. I think when we look at visual recognition, this may be difficult. It could be translational invariance. This is fairly obvious that if I want to recognize an object, it should be independent of where it is. But I think one of the big challenges is that often we do not know what the invariance group is. Do you see ways to infer the right invariance group from observations, from examples?
Yeah, we are working on that a little bit. So, I mean, first of all, you can do data augmentation. So you can sort of try to come up with the actual transformations on your data that you observe. This could be if you're looking at videos or time sequence data. Then you can sort of see in the time sequences that certain transformations happen. For instance, if I rotate my head, and I do this obviously a lot, then I see the world transform all the time in a very particular way, and I know that these things come smoothly usually if I move through the world, right? So these 3D transformations in my visual field, I see a lot, and it's not strange that our brains have figured out how to adapt to those transformations, right? And I think so. The way that we are exploring this is to try to basically learn efficient representations that sort of encapsulate, in some sense, these transformations that we observe in dynamical data in capsules, in the sense that Jeff Hinton has defined capsules, which are very similar to the way we define our feature maps. So that we have feature maps that transform in certain ways under, so if we have representations, then typically what we say is that we define, let's say, a permutation, some kind of permutation on those feature maps as I transform, let's say, my input space. So you could sort of do something like I force my my transformations in my capsule to take a certain form that I can define myself, and then I can apply my transformations on the input space, and then I can sort of put regularizers on my learning problem, so that if I see these transformations that happen over time, they get forced onto these particular given transformations that I want to happen inside my capsules. And that way I can sort of I can learn my own kind of equivariant map.
Would this approach also be able to somehow model not invariance but robustness? Somehow I think if you look at the visual system of humans, it's often not fully invariant to certain transformations, but let's say robust. For example, if I see a car in different rotations, I will still recognize it as a car, but if it's exactly 180 degrees flipped, upside down, I would typically take much longer to see that it is a car. So I think even the human recognition of objects is not invariant to rotation, but let's say robust to rotations.
Yeah, well, so the thing about equivariance is that it is precisely not the same as invariance, right? So you can think of equivariance as basically having two components to it. Mm-hmm. One is perhaps, if you want, sort of an invariant part, which is basically the presence of the object or something like that, which is the total activation that that's happening inside one of these capsules. And then you have sort of the actual detailed activations that the neurons have inside this capsule, which tells you, the actual orientation, right? Now, if you need to learn, if you need to sort of predict invariant things, like, let's say, is there a car, yes or no, then you need to pool over all the activations inside the capsule, which basically means you look at the total activation that's happening inside that capsule, irrespective of how these activations are distributed inside the capsule. Now that is an invariant, and that's, of course, and you don't have to do this in the beginning of your neural net, because if you do it in the beginning, you lose all the pose information, right? You can do it at any level later down. So you want to typically keep all the information as you process, but you want to disentangle this in such a way that at any point in time, you can just build your invariance by integrating over the full activations inside a capsule. So I would say that gives you a certain level of robustness, but it will not commit to complete invariance in the beginning, because if you do that, you get this kind of what we call Picasso effect, that you know, a bag of nose, ears, and eyes, and basically a bag of edges is just as probable to describe a face as if one where they precisely come in the right sort of constellation. And of course, that's not really what you want.
Okay, thank you very much for the answer. We would also have some questions from YouTube. So Sidan Katayan asks, how can we generalize CNNs to Riemann manifolds, for example, the Stiefel manifold or the Grassmannian manifold?
Okay, so these latter ones, I would really have to dig into. They sound very exotic. We did actually do precisely the extension to Riemann manifolds, because Riemann manifold is not as exotic as maybe the Grassmann manifold, I think. But so for the Riemann manifold, you basically the top, we call it gauge equivariant neural networks. And you have to first define what it means to do a convolution. It means that you have to define how to take a particular, how to share a feature map or a kernel. And we do the actual, so basically what you have to do is you have to, for any point, you have to use the logarithmic map to take the points on the manifold and map them back onto the tangent space. And in the tangent space, you can then do your convolution. That's one issue. The other issue is that there is actually intrinsically impossible to define a canonical frame on, for instance, a sphere. Because if you go into a circle, your kernel is rotated. And so you cannot say, forever, that the kernel is oriented in one particular way as if you would do it on a Euclidean space. So you would have to basically have steerable kernels on the rotations, let's say, on a two-dimensional Riemannian manifold, so that you can sort of always relate one result back to another result. So the result cannot depend on a particular choice of frame, but basically it has to be equivariant precisely under SO2 rotations. The choices of the frame are SO2 arbitrary. And you have to be able to always relate one result back to another result which is rotated relative to it. So it's called gauge equivariant neural networks, and it's basically a full framework to do these convolutions on a Riemann manifold.
Okay, thank you very much. I think we have one second question from YouTube from Hannes Sterk, and he asks, for the EGNN paper, for the QM9 experiment, you don't update the coordinates. So is it just an MPNN with pairwise distances as edge features? How do we get soda performance with that? And what is he missing?
It's a very good question. So it shows that the X person read the paper. It is true that for that particular application, because the molecule isn't changing, right? So the point there is really that the molecule, we just have to predict a bunch of features of the molecule, but it's not evolving, right? It's not like a molecule that sort of folds, right? So if it would be something that folds itself, then you would have to update the positions X. In this particular case, it's just a very powerful GNN plus invariant features like the distances, and that's of course equivariant or invariant, in fact. And that's already giving the very good results on QM9. And what we have seen basically is that the relative to other graph neural networks, the particular implementation that we had, so a lot of the improvement for this particular application came from the fact that we had a powerful GNN. And then of course the distances do contribute, but equivariance or moving the actual positions around did not deliver us anything. Of course, for the other experiments where things are moving, it did actually matter a lot to have that, but for this particular one, it didn't matter.
Max, I wanted to follow up on the work you did on the molecules, and one aspect of how you achieve this equivariance was that you consider the distances, right? And because these are preserved under rotation. But another thing that's obviously preserved under rotation is the angles between, if you, let's say you have three elements in a molecule and you rotate, and the relative angles remain the same. Can you capture that as well in your representation?
Yeah, so so that's a good question, but in most people add the actual angles as additional sort of features on triplets. That's actually quite expensive. So what we do here is, if you extend, let's say, if you not just send messages over the edges of the molecule graph, but also send messages between nodes, let's say, that are 2 hops away. So now you have an actual angle, right? And now you have the vector difference xi minus xj and xi minus xk, right? They're both encoded as vectors, not as just distances, but as actually vectors in the E, G, and N. So it's not just invariant, it's an actual equivariant representation. And so as you go farther away, you also encode all these angles between the things that are further away, because you actually maintain not just the the distance, but actually the actual full distance vector. So it's actually a very good point, because so as you go further away, you automatically capture the full structure of your neighborhood, including all the angles, and even between more complicated angles between, like let's say, things which are 3 hops away. You could easily encapsulate that as well. Yeah.
Thank you. Do we have more questions?
Yeah, it's actually time. I have another meeting coming up soon, so
I think that's good. Very well. I just wanted to make sure there's no other questions. Thank you so much, Max, for the wonderful presentation, and also for the exciting discussion following. Thank you so much. It was a pleasure to have you with us today.